All right, hello class, and welcome to lecture 17, where we're going to delve a little bit into logic, I suppose, deductive reasoning, and talk a bit about the basic question, how we enforce inequalities on sets. So, I suppose to begin, we should recall way back in lecture 3, I think it was, we had this duality between the geometric and the functional representation of an optimization problem. So let's see if I can write this up here, or maybe I'll write it down here. So we had, if you remember, maybe we're doing min, I think, of f of x over x, such that, let's say, g of x is greater than or equal to 0. And we talked about how this functional representation could be alternatively written in the geometric form, although we gave two options there, right? So partial geometric and full, min over x, t, such that t is greater than f of x for all, on the set g of x greater than or equal to 0. So we had, we moved now the objective function into the constraint set. And then we went a bit further and went to a full geometric representation x comma t of t, such that the set that t is less than or equal to f of x, g of x, actually the greater than, the set x comma t such that t of greater than f of x, g of x is greater than or equal to 0 is not infeasible. So there's a point x such that that's true. So this is the geometric, and this is the functional representation. And then in the last lecture, we argued that there's a that sort of what we're looking for in these Lyapunov inequalities, where we're trying to enforce v of x greater than or equal to 0 for all x in a set, say for example like that. Right? This optimization of polynomials question, right, was dual to this optimization problem, where now we're looking for max, not min, max of t, where t is a lower bound on f on the set, right? So max t such that t is less than or equal to f of x for all x in all x, such that, let's just get the set, g of x is greater than or equal to 0. Right. So in here, let's rewrite it a little bit. F of x minus t is greater than or equal to 0. And so we argue that we want to now enforce positivity of a function on a set. And in order to do that, we require certificates. Well, we can actually take this a little bit further now, right, and go a step further and make this a full geometric representation. We can go even further. We can say max of t such that this set, it's exactly the same problem here, but with this one, but that now we require the set is infeasible. So max t such that the set t greater than or equal to f of x with g of x greater than or equal to 0, that x comma t such that that is infeasible. So in the optimization of polynomials framework, there's also a geometric representation where we've moved, it's exactly the same problem, except we've replaced feasibility with infeasibility. This is feasibility. This is infeasibility. Feasibility. Okay. And we argued then in the last lecture, right, that proving actually the feasibility problem in some ways is harder than proving the infeasibility problem, even though these are sort of dual problems, right? One is equivalent, well, the objective function is equivalent to in both cases. In the feasibility case, you actually have to find a point. The only way to prove feasibility is to find a point such that this set these inequalities are satisfied. The infeasibility case, however, is ostensibly harder because, right, you have to prove that this is infeasible, right, that there's no x, right? And how do you, that's a problem, but it's convex. That's a convex problem. The problem is how to certify that. And so we argued that the one way to do that is to come up with like squares, sum of squares or rational squares or something like that. But that was, of course, only on the function, and now we have two inequalities here. So we have to prove infeasibility of a set with two inequalities. And, well, is that harder or is that easier, right? So in general, the problem now is to prove that f of x is greater than or equal to 0. That's a 0. For all x such that g of x is greater than or equal to 0. Right? So, but that problem is equivalent now to infeasibility of a set. F of x less than 0, comma, g of x greater than or equal to 0. Right? That's equivalent to infeasibility of that set. So how do you prove that a set is infeasible? Well, one could look at it and say, for example, if the set said something, one of the constraints was like -1 is greater than 0, well, that's clearly infeasible. So is that, what can we go further than that? Is that necessary and sufficient? Well, it turns out that the issue at hand is really the part of the representation of the set itself. So how we define the set is equivalent to, or in some ways is equivalent to feasibility of the set itself. So if we can, for example, use deductive reasoning to prove that -1 is positive, well, that is a proof of infeasibility. Similar to the existence of a sum of squares representation, a squared is positive, so that's proof of positivity, so the converse. So we'll see in this lecture that there's this question of what the set says, like what are the logical conclusions, and when we're looking at questions of infeasibility, one of the questions will be whether a conclusion ultimately is that, say, something ridiculous happens, that -1 is greater than or equal to 0. And that's in the same way that we had duality between the functional and the geometric representation. This set infeasibility is sort of the dual of sum of squares. So this problem was sum of squares, and this one is infeasibility. And they're equivalent in that dual sense. And we'll see as we go on, right, that there's this question of whether it's easier to enforce questions like this, or is it easier to enforce questions like that. So, sorry, that was a long-winded introduction, but hopefully I haven't dissuaded you from watching the rest of the lecture. But I do want to say, right, this lecture is rather abstract and is rather mathematical in that sense, and that we're talking about sort of fundamental questions of deductive reasoning and how one proves things through certificates, right? Certificates are basically obtained through deductive reasoning. And so we're going to go through sort of all the ways, well, in sum of squares for positivity, we went through all the ways of deducing positivity. And in this case, we'll be looking at how to deduce infeasibility, right? So that will be taking basically the same approach. In any case, the introduction aside, now we're looking at local questions, right? Questions of local positivity, local negativity. So, for example, the basic Lyapunov question, f of v of x is greater than or equal to 0 for all x in a set, not all real numbers, and v dot of x is less than or equal to 0 for all x in some set, right? And so that's a primal version. Of course, you can construct the the infeasibility representation, the geometric representation of that as well. And the reason, of course, for that is because most nonlinear systems are not globally stable. For example, when we formulated our optimization of polynomial questions in lecture 15, I believe, for example, we were looking at whether the Lyapunov function is decreasing outside of some set, so in some region outside the set. In the van der Pol oscillator, we were looking for a Lyapunov function which was decreasing in the reverse time, at least, right? Inside some set, inside the unit ball is what we usually took. But in any case, both of these are not global. They're local positivity and negativity questions. And so obviously we're going to be looking for how to enforce those types of positivity and negativity conditions. Some other examples, that some of which we went over earlier and some of which we didn't. The matrix copositivity question, right? The question of whether this quadratic form, very simple quadratic form, is positive on the set y greater than or equal to 0. And notice that in all of our cases, right, our sets are defined through inequality constraints. On the first slide and in this slide as well, right? They all have this sort of form, g of x, or g of y in this case. I should use y such that g of y, that's a g, that's a y, greater than or equal to 0. Right? So we're looking for positivity on sets which are themselves defined by positivity constraints, and we'll be using that important property of how we define these sets later on, very shortly. Again, but I wanted to call your attention to it now. And then again, we have a new problem, right, which is this question of integer programming, which is a very hard problem, by the way, NP hard. But which actually we have very good algorithms which solve it approximately, but not exactly. But in any case, in this case, integer programming, we're finding the maximum of an objective function. Here we've moved the objective to the constraint set, right? In the same way that we use the half geometric interpretation on the first slide. So geometric representation. So we want to find the minimum of gamma such that gamma is greater than f of x for all y in this set, negative 1, 1 to the n. And this is actually sort of a simplification of the integer programming problem. We can make that, expand that. That would be y equals negative 1 or 1. Notice that it doesn't have this inequality representation that we have right here, right? But actually you can express this as an equality by the constraint y plus 1, y minus 1 equals 0, I believe. So the only two solutions to this are y equals negative 1 and y equals plus 1, right? And so there's a bunch of those. So this is an equality constraint. So we've added, like, now equality constraints to the mix. But of course, equality constraints can be defined by two inequality constraints. So we could just add two constraints, greater than or equal to 0 and less than or equal to 0, and we'd get the same thing. And then, of course, we have the local Lyapunov stability criterion, v greater than 0, or x squared in this case, on the unit ball ball of radius 1, and that the derivative, v dot, of the Lyapunov function is decreasing also on the ball of radius 1. And again, clearly, these sets on which we're enforcing positivity and negativity are defined by inequality constraints. So in all our cases that of sufficient interest, I think, most of our sets can be represented, even if they're not maybe a priori represented in this case, but they can be represented as inequality constraints. And so we are going to focus our efforts in this lecture and all previous subsequent lectures on positivity and negativity of sets which are defined by inequalities and equality constraints. We can allow that as well, since it's a special case of inequality constraints. So these sets have a very specific name. They're called semi-algebraic. And semi referring to the inequality constraints. Inequality constraints, and algebraic actually referring to the fact that the inequality constraints are defined by polynomials, so that G here is a polynomial. So all of our sets satisfy that. For example, this is a polynomial, right? This is a polynomial, a very simple one. It's just linear. This is a polynomial because this is x squared, or x transpose x, which is a sum of xi squareds. So all of the cases that we considered so far are defined on semi-algebraic sets. So we're going to restrict ourselves going forward to those types of sets. So specifically, we'll define formally here the definition of a semi-algebraic set. So a semi-algebraic set is one, very simply, which is defined by a finite number of inequality constraints, where the left-hand side here are all polynomials. Right. That's a very general representation. In, say, the S-procedure, for example, it was defined by quadratic forms. Remember the S-procedure, x transpose f x greater than or equal to 0 for all x such that x transpose g of x greater than or equal to 0. That was the S-procedure. And of course, the robust stability conditions were all defined in terms of semi-algebraic sets as well. And so semi-algebraic sets are sort of just as general as we allow. Well, we can't get perfectly general, but they're general enough to encompass all the cases that were of consideration in this course and probably many other courses. So I note that there's some definitions of semi-algebraic sets, which include not equals to signs and strict inequalities. We're going to try and avoid those just because most of the results that we have don't account for or are not expressed in those terms. But you can, of course, use those here. So we're going to avoid strict inequality constraints. So we allow 0. And then not equals to. That's like everywhere except for equal to 0. So we don't. We're gonna not use those. So as I said, the discrete values case, right? If you actually multiplied out that polynomial, right, you get y squared minus 1 equals 0, or equivalent to yi squared equals 1. The unit ball, right? X transpose x is less than or equal to 0. We, of course, move all the non-zero terms over to the left-hand side, so that's why, and actually we move them over to the other side because we have we want to make them greater than or equal to 0, and this is less than, so we have to move that one over there. So 1 minus x transpose x is greater than or equal to 0. So this would be an example of a Q, and this would be an example of a P. And of course, it's important to note, and this is going to be a theme throughout this lecture, is that these representations of the set are not unique, right? So this is one representation of a set. For example, the discrete values, there are multiple possible representations of that set. For example, you could just you can multiply 2 times the whole thing, right? And then it would be the same set, right? So you multiply 2 times y squared, and obviously has the same set of roots. So the representation of the set is not unique. And in fact, actually, you could go further, right? You could like write yi squared plus 1, multiply that through instead of 2, and it would be the same set. So there's lots of different representations of the set, and that will be an issue going forward that we're going to be thinking about. What is the correct representation of this set, and why does it matter? So, but it's a little bit early to do that. Here's a nice example that was forwarded to me by James Forbes at Michigan, and it's just it's a matrix value differential equation where it's a dynamics of a rotation matrix, so that's interesting. In spacecraft dynamics, this is on SO3, the special orthogonal set 3. And so it's got 9 variables in it, right, because these are the rotation matrices. But it has the constraint, so these are the dynamics, but it has to be stable only on the set of rotation matrices, right? So how do you quantify rotation matrices? So this is an interesting example of an algebraic set, right? Algebraic set. Right, because the necessary and sufficient conditions for it to be a rotation matrix are that C transpose C equals the identity matrix, and the determinant of C is equal to 1. So if C is our variables, right, this is a H1 of C, I guess. So let's use a vector version of C. Vector version of C. So where you take all the columns and you stack them on top of each other, like we talked about in the previous lecture. And then the det of C, right, is we know how to calculate det, although it's rather complicated. But in the end, you get a polynomial, right? Both of these are polynomials. Right? So you can actually represent the constraint that a matrix be a rotation matrix as an algebraic set. So that's interesting. So maybe we were interested in doing something like, again, this is vector's version of C. Maybe you're interested in determining Lyapunov stability of a rotation matrix, and then you'd have to prove that v dot is less than 0 on this set of rotation matrices, which is itself a semi-algebraic set. So that's interesting. Just threw another example in here. Right. So let's recall the results from the previous lecture. So this considers a special case where our set is all real numbers. Right? So how do we construct representations of this set? So certificates, right? We show that P is positive if we can use some kind of deductive reasoning to prove it is, right? So if, say, for example, P is a square, right? Then squares are positive, therefore it's positive, right? If it's the product of squares, right? Deduction, S is positive, S2 is positive, therefore positive. Sum of squares. S1 is positive, S2 is positive, therefore this is positive. You add a positive to a positive, therefore the result is positive. Deductive reasoning. Squared, squared, add squareds, right? Only two simple rules. Products of positives are positive. Sums of positives are also positive, right? And then, of course, we have the third one, which we don't think about very much in this course anymore, which is ratios of sums of squares, right, are positive. Right, so if S is positive and you divide by a positive number, that's also positive. Right? This is, of course, Hilbert's problem, Hilbert 17. Of course, in this course, we mostly ignore that, this ratio of sums of squares, but it's important, actually. When we talk about the equivalent for local positivity, we're also going to have to include those ratios as well, right? In certain circumstances. In some cases not, but most cases yes. So now this is the reasoning behind sums of squares, right? We're taking squares, which we know to be positive, we're adding them together, multiplying them, and we search over the set of all such inferences. So this constraint allows us to search over the set of inferences, set of deductions from the basic premise that squares are positive, products of positives are positive, and sums of positives are positive. From those three premises. Well, actually 4 if you include the ratios as well, so I'll add 4 premises. So now when we go to local positivity on some set, we're also going to have to come up with a set of premises and see if we can search over the set of all possible deductions from those premises, right? The set of inferences. So let's set the stage. So let's consider the S procedure. What did that do, right? How did that work? Right. So in this case, we were looking for positivity of this quadratic function, right? So this is our f of x. On a set, again, it's a semi-algebraic set defined by a single polynomial inequality, which was quadratic. G of x is greater than or equal to 0, where g of x is x transpose g of x. So how did we know the theorem states that this is positive on the set if and only if there exists a scalar tau greater than or equal to 0. There's a scalar positive. Such that f minus tau g is greater than or equal to 0. So this is what this inequality states, right, is that x transpose f minus tau g x greater than or equal to 0. Oop, that's not 0. For all x, right? So positivity of this function on this semi-algebraic set is equivalent to global positivity now of this function here. So how does this work, right? So the sufficiency argument, for example, goes like this. Well, I'm not going to go over necessity because it's complicated. But sufficiency works like this, right? We know tau is positive. We know z transpose gz, g of x, z actually, is positive on this set. This is positive everywhere. Everywhere. This is positive only on the set, but it's positive, right? And hence, deductive reasoning, if we multiply a positive thing by another positive thing, the result is also positive, no matter what tau is, as long as it's a positive constant. So if, right, the inequality is satisfied, and this is sufficiency here, if this inequality is satisfied, then the function z transpose f of z, right, you multiply both sides by z transpose z, and then we have on the left z transpose f of z, and on the right tau z gz, and our inference is that tau is greater than or equal to 0. This is greater than or equal to 0 on the set, and so the product of this is positive on the set. Right, not everywhere, just on the set. And it turns out that in the case of quadratic forms, this is necessary and sufficient, with some small issues like strict feasibility, but in the vast majority of cases, yes. So what have we done here, right? So it's similar to sum of squares in that we're multiplying two positive things, but the big difference, and in fact, perhaps the only difference, is that now we're also multiplying by something which is only positive on the set. By something, and we're not really searching for this, right? This is it's given by the definition of the set, and now you sort of you get the idea of why representation of that set is important, because that representation plugs directly into sort of this sufficient condition right out here. So if we were to take this to polynomials and sort of apply it to polynomials, the result would be, well, okay, if our set is defined, or if we're looking for f greater than or equal to 0 for all x such that g of x is greater than or equal to 0, right? Then if f of x equals something equals g of x, right? If f of x equals g of x, then obviously it's positive, right? Because on that set, because that's by definition, that's the representation of the set itself, right? But we, presuming that f of x is not precisely equal to g of x, we could add something which is positive everywhere, or multiply it by something which is positive everywhere, and that would be a valid deduction of things which are positive on the set. And then, well, so if we stop there, we'd have the S procedure, right? But we can go a little bit further because now we know how to parameterize sums of squares, which we know are positive everywhere. So as opposed to just using a scalar tau, which is positive everywhere, we use a sum of squares. And of course, a scalar is a sum of squares itself, so it's more general than the S procedure. And so if we were just to come up with the most obvious generalization of the S procedure to polynomials, we would require that f of x equal to g of x times tau of x, right? But of course, we're forgetting about the inequality here, right? Greater than or equal to 0. So actually, what we would like to do is move this term over to the left-hand side, so it looks like that, and then say that's greater than or equal to 0 for all x, right? Just as we do here. And then, of course, we have to prove that somehow, and so we can use the sum of squares results on the previous slide to say equals s of x, which is sum of squares, right? So we've added two sum of squares variables here and here to the problem. It's linear in those variables. In fact, actually, I should start highlighting our variables here, right? Those are our two variables. G of x, however, is given, right? It's not a variable. And so, but this is a relatively straightforward condition for positivity. It's one we can already enforce just using sum of squares, right? We SOS tools or something like that. We say equals to s, which is sum of squares, right? This is the main idea, actually. This is in fact in many in most of the results we actually never go further than this condition, because it's enforceable, it's a sufficient condition, it's a generalization of the S procedure, so it's pretty good. Except when it's not. And when is it not? So in the quadratic representation, or in the matrix representation, this representation of G is not, there's not a whole lot of flexibility in that. There's pretty much just one representation, and that's like necessary and sufficient. Of course, in semi-algebraic sets, however, unfortunately, there's lots of flexibility, or fortunately, in how we represent the sets. And so this may or may not be an accurate test depending on G, on how you chose it. Important for accuracy. And it's very important for accuracy. If you choose the wrong G, this sufficient condition won't work at all. Say, for example, if you have the interval 0 to 1, for example, and you choose G1 to be x greater than or equal to 0, and G2 to be x less than or equal to 1, that you have two constraints, and you can make a multiplier for both of them, of course, but that's not going to get, it rarely works in the case, at least, of Lyapunov functions. So the main idea, right, and this is actually something of a statement of Poutenard's positive Stellan sets, is to enforce positivity by searching not just over the set of sums of squares, which we included before, which are products and sums of squares, right? So they're all positive and they're deductive. We're going to add one more term to this, right, which are terms which define the representation itself, g of x greater than h of x. And these are terms which we know to be positive on the set, and this one, of course, is equal to 0 on the set. So actually, when you include h, right, this is equal to 0. So you multiply anything by 0, and it's still 0. And so actually, this doesn't change the function itself. And so if this is positive, this is positive, this is positive, this is 0, right? So we have two sort of new inferences, right? If we now take products of G, which are positive on the set, local positivity, and then we also add terms which are 0, that's also positive, right? So sums of squares, products of squares, products of the representation itself, and terms which are 0 all deductively infer positivity. So we're adding positive terms, positive terms, positive terms, anything and 0. So basically this whole thing is equal to 0. So adding zeros doesn't change positivity either. So again, right, this is a way of constructing inferences, a way of deducing positivity by combining things which we know are positive in some basic premises, which are that squares are positive, sums of positive terms are positive, and the representation of itself, of the set itself, is positive on the set, right? By definition. But the question is, as with sum of squares, is it necessary, right? And remember, for sum of squares, we needed those ratios, right, which we're not including here. And the answer is sometimes, right? Sometimes. And to answer that question, we're not going to turn to it right off. We are going to delve into certain sort of deep theorems which tell us when, how deep we need to go in terms of inference before we get a condition which is necessary and sufficient for positivity. And those are referred to as positive Stellensatz results. And actually, we're going to cover that in part B of this lecture, which will be rather short, so don't get too concerned there. But anyway, positive Stellensatz, we'll talk about it later, means theorems which prove positivity on local sets, basically on a local area. Right? But they're how well these types of conditions work. Right? These are SOS conditions. But how well they work depends very strongly on how you've chosen your G and your H. And so really the positive Stellensatz tells us things about what's the right way of choosing G and H. Right? So we get to that. Right. But before we get to that, let's go into these questions of inference a little bit deeper. So the question of how you represent a set is not fixed, right? There are lots of representations of sets, and some are easier to deal with than others. Sort of like in polynomials, right? We had quadratic and linear representations, although that analogy is rather specious in this case. But in any case, we'll start with linear and quadratic representations, just to make the analogy. So say we're just interested in this set A to B, an interval. Right? Very simplest set you could possibly think of, maybe other than a half space, right? So an interval on the real line, A to B. And we want our Lyapunov function or whatever to be positive on that set. So the problem we've stated is we want v of x, I don't know why I keep drawing for all, v of x to be greater than or equal to 0 for all x such that g of x greater than or equal to 0. And now what do we choose as our g? Well, we could do two things. We could choose two g's, right? This is the most obvious one, g1 and g2, where g1, right, is x greater than or equal to a, and g2 is x less than or equal to b, right? So that's the most obvious representation of the set. It's greater than a, and it's less than b, right? This is a first order. We'll call the first order representation, because all of the degrees of g are 1 in this case. They're all linear. These are linear functions. However, it's not the only representation, obviously. And let's think about how we can change the representation without changing the set. So for example, we could multiply these two terms together, right? So we could have x greater than or equal to 0, x greater than or equal to b, x less than or equal to b, and we could take the product of those two, right? So that's g1 and g2, right? Right? And if we combined all three, right, that would also be a representation of the set, because it would, on that set, right, x is greater than or equal to a, x is less than or equal to b, and therefore this product is also greater than or equal to 0 because both of the parts are greater than or equal to 0. So this is an equivalent representation where we've added g3. It turns out, though, that actually if you include g3, you don't need g1 and g2, well, which is rather surprising. If you would just draw the quadratic, it looks like this. If you draw g3. And in fact, actually, g3 is positive only on the set. So actually, now in the quadratic representation, only using g3, we can represent the same set with a single inequality, g3 of x greater than or equal to 0, which precisely characterizes the set. It's an equivalent representation, but only uses one g. Of course, the price we have to pay for that is that g3 has a slightly higher degree. And so which of these sets is better? Right? Maybe this one's better because you had two multipliers, right? So that seems like it gives you extra flexibility for things that are positive. But this one only has one, right? So is that more accurate or less accurate than this one? Is this going to work better with our results on the previous slide or worse? Well, we could go further, right? I mean, we could combine them together. So we could use G3 and we could add in G1, right? That would also be an equivalent representation of the set, right? So obviously. We could add a square to it, right? So maybe that will help. If we increase the degree once, we can do it again. We could just add a square to it, and right, this is g3 here, right? So that's positive. So we can multiply g1 times g2, and also by some random square, s of x squared, right? Sum of squares, actually, because there's two of them. There's 1, 2. And that would also be an equivalent representation of the set, right? Now, we could go further. We could combine all three, right? We could take G3 there. We could, wait, I have G3 twice here for some reason. We could have, well, sure, we can have G3 twice. Why not? We could have G3 times x, or s squared, sum of si squareds, right? Again, so you can see, right, these are all valid representations of the set, right? And in fact, we could go on further, right? We could add any function which is positive on that set to the representation of the set, and then it would be an equivalent representation of the set. Now, this is important because, right, if you keep adding these terms to the set, and keep adding these like positive terms to the set, right? Remember what sort of one of our basic conditions, right? If f of x equals to gi, some gi on that set, right? Well, then it's obviously positive, right? So actually, if the function you're looking for is included in one of the representations of the set, then you're done. So as you add terms to the set, right, at some point you might just be done, right? You might just get the function back yourself, right? So the question of representation of these sets is really what we're going to be focusing on, because that is actually the question of how well the sum of squares works. And so when sum of squares for local positivity doesn't work, it's usually because you have a bad representation of your set. But understanding what is a good representation of a set is really, really tricky. And that's why we have positive Selin sets. So what's going on here, right? We're constructing valid representations of the set, right? And how are we doing that? Well, we're adding redundant constraints in a way. So if this is your set, right? Here's your set, for example, right? and it's defined by certain inequalities, right? C1, C2, C3, C4, C5, right? We could always add a different constraint. We could always add CW here, or something that's not even touching the set, right? It's not very tight at all. CR is greater than or equal to 0. Right? And those would be perfectly valid inequalities, and we could add them to our representation. So the question is how many of these we should add, and when should we stop, right? In the case that we considered on the previous slide, of course, we considered sums of squares, which are positive everywhere, so obviously they're positive on the set. We also added combinations and products and sums of the original representation of the set to get additional constraints to the set. So, for example, if we added the multiplication of C5 times C1, we would get a valid inequality on the set. It wouldn't be linear, but it would be quadratic, and it would be valid. Right? So, in a sense, the question of whether a function is positivity, if we come back to that pure geometric representation of the optimization problem, the question of whether a function is valid on the set, is positive on the set, really comes down to whether it actually can be used as a representation of the set itself. Whether it is a valid constraint on the set itself. So if we can add it to the set of constraints on the set without changing the set. So the positive Stellensatz results that we're going to go through are basically determining whether f itself is a valid constraint on the set. So it's going to use these rules of inference, use these rules of deduction to search over all valid constraints on the set and then determine whether f is one of them. Right? And so the question that we answer with these positive Stellensatz results is how many of these these deductions do we need to use before we come up with a necessary and sufficient condition for positivity on the set. So let's start by defining a few things. Right? So let's make that question that we posed on the previous slide quantitative. Right? So we'll consider a function, right, to be a valid inequality, just by definition, if it's positive on a set. So given a set, a function is a valid inequality if it is positive on the set, which is obvious, right? So, but we should go ahead and state it anyway. So we haven't defined rigorously what a valid inequality is, so there it goes. So then the next few slides consider how we come up with these valid inequalities, right? So obviously, as we argued earlier, right, if you have two valid inequalities, and here we get away from the term positivity, we can talk about valid inequalities because, right, they're not positive everywhere, only on the set, so we use the term valid inequalities. So similar to sum of squares, right, if f1 and f2 are valid inequalities, or valid, then you add them together, that's also valid. Right? It's all deduction, right? Positive on the set, positive on the set. You add two positives together on the set, it's positive, right? So closed under addition. Multiplication works as well as for sum of squares, right? If f is a valid inequality and f2 is a valid inequality, you multiply two positive terms, which are valid on the set, together, and it's also positive on the set, right? So the set of valid inequalities is also closed under multiplication. And now we've got the third one, which is that anything which is positive everywhere is also, of course, positive on the set because it's positive everywhere. Right? So we can add to these two conditions the sets of sums of squares, right? Or actually, all we need to do is add the squares to the set closed under squares, right? Because, of course, when you multiply and add things, you get sums of squares, right? So any square is valid on any set, right? No matter, it doesn't matter what G is, and it doesn't matter what the set is, right? So we're just basically going to examine these inferences. These are the three inferences, three ways of constructing valid inequalities that we consider, right? And so on the next slide, we define, right, something which is called the cone, which is a set of all valid inferences based on your inequalities. Right. So specifically, we define something called a cone. And note that this is not the same definition of cone we use in optimization. This is this definition of cone they used in algebra. In algebra. So this is the algebraic definition, not the vector space definition we introduced much, much earlier. So it's a different definition. Right, highlight it. This is not a cone in the same sense that we talked about it in geometry earlier. First of all, it's defined on polynomials, right? So we say a set of polynomials is a cone. All right, so it's only defined for polynomials. So we define a cone as a set of valid inferences, right? So it's a cone if for any f1 and f2 in the cone, if you add those inferences together, it's also in the cone. If you have two valid inequalities or two functions in the cone, you take the product, it's also in the cone. And the sums of squares is also in the cone. So this is the set of polynomials you can combine together to get a set of valid inequalities. Right? So it includes that addition property, closed under addition. It's closed under multiplication, under addition, closed under multiplication, and contains the sums of squares. Right, so there's three types of valid inferences that we talked about on the previous slide. It's not, of course, actually a cone because of this algebraic thing, right? It's closed under composition, which when we have vector spaces aren't algebras, so it doesn't even make sense. It only works for algebraic sets. So now we consider the cone, which is a cone, but we call it the cone. I don't know if you can see it. This is italicized. The cone, C of S. Right? It is a cone, but it's broad. It's not just any cone. It's the cone, right? So this is a set of valid inequalities. It's the cone of valid inequalities on F, right? Or sorry, on S. Right? It's on S. This is the set of valid inequalities. So really, it's just this definition is nothing more than the same definition of valid inequality, but it's just we take the set of valid inequalities. However, right, it is a cone. Because of the properties we talked about earlier, right, that take two valid inequalities, add them, multiply them, add squares, right, then you get, it's closed. So it is a cone in the definition, using the definition on the previous slide. And it's a set of all valid inequalities. And so when we're talking about positivity of a Lyapunov function on a set, right, we're really asking the question, is V a valid inequality, which is equivalent to, is V in the set of valid inequalities, right? So V is positive on the set if and only if just by definition, this isn't really a corollary, it's just a definition, if F is in that set, or if V is in that set. This is necessary and sufficient, it's just by definition. And so the question, of course, becomes, how does one test whether V is a valid inequality? So computationally, right, let's try and construct, using our set of three logical inferences, some sets of valid inequalities. Not the set, but proposed sets, right? So the first one is what we refer to as the monoid, right? Definition, monoid. This is a finite set, right? So if our set is defined by these inequalities, x such that gi of x is greater than or equal to 0, right? The monoid is the product of all of those valid inequalities, right? So if this is our set, right, then obviously, each of the gi's are valid inequalities, right? Clearly, but just by definition, right? So the monoid then is closing the set under products of those valid inequalities without including sums of squares quite yet. So this is closing these valid inequalities, starting with the definition of the set itself, under multiplication. So we just basically take each of these valid inequalities, which come from the definition of the set itself, and we multiply them together. So we include G1, that's in the set, G2 is in the set, and then products, G1, G2 is in the set. And then actually we go a little bit further in the monoid and we allow powers, right, of those sets, right? So the product of all of the representations of that set, the sort of the prima facie valid inequalities of that set, and then we take powers of them as well as products, right? So, for example, G1, G2 squared is in there. G1, we could also include G2 cubed is in there, right? Now, don't get too excited about those products because basically all they're doing is allowing squares, right? So those are things we already knew were positive. So it doesn't add that much in that sense. One thing it does add, though, is 1, right? Because if all the powers are 0, right, then we get back 1, right? So 1 is in the set, always. Right? So obviously 1 is positive everywhere, so we shouldn't get too excited about that. It's not particularly exciting. What I do want to say is, right, this does not include arbitrary sums of squares, right? So, right. If f has to be part of the representation of the set in order to be included here in our squares, right? So it does not include SOS, right, at this point. It's fine. Well, it's not actually finite because we don't have actually a bound on these degrees, but it's at least countable. And if we actually make all the degrees just 1, right, it would be finite, right? So all possible products of these terms is finite, right? So if we have G1, G2, G3, then we just need to include the monoid would consist of 1, G1, G2, G3, obviously, and then G1, G2, G1, G3, G2, G3, and then I think we're done. And then, of course, higher powers as well. But those are the basic terms that we need to include. So if we stop at finite powers, right, then this part of the monoid at least is finite, right? So we don't have to go any further than that. If we modulo the squares. Okay. So there's no optimization problem in that one, right? There's no arbitrary sums of squares. We know what all the GIs are, so it's fixed. The monoid is fixed, right? So that's the monoid includes the previous two inferences. It includes sums of valid inequalities and includes products of valid inequalities, so rule 1 and rule 2. And now if we include the third induction rule, which is add sums of squares to it, which are positive everywhere, we get another set which is referred to as cone. And here I write it to avoid confusion as in this sort of text TT characters, MATLAB characters. This is a different cone than the one we had before, right? So basically it includes all terms in the monoids, right? But it adds sums of squares as well, right? So it says that a function is in the cone of a given set of polynomials. So these fi are given. And usually they're given by the representation of the set itself, right? So you have the representation of your set, and then you use that to construct the cone of those polynomials. And so that comes from, right, the GIs, right, everything in the monoid, and then the products of everything in the monoid with sums of squares, right? So and of course the sums of those terms as well. So this is the monoid was taking terms 1 and 2, those inferences, and then when we add sums of squares, we get the cone. Right. So it's important to note that, of course, because we're only using those basic 3 rules of inference, every polynomial in the cone, and of course in the monoid, but that's more restrictive, every polynomial in the cone is a valid inequality. Right? So the cone is a subset of the valid inequalities. That's the valid inequalities, recall. However, the question is whether it's a strict subset, right? Is this strict, right? If are there any valid inequalities which are not in the cone? In C of S, which are not in the cone. Right. Assuming, of course, C of S is defined defined by the FIs, right? So that's an assumption. The important part, of course, is that, well, it's not possible to test over a set of all valid inequalities because it doesn't have a computational form. It is possible to test using sum of squares whether a function is in the cone, right? Because now we know how to optimize over sums of squares, and so these become our decision variables. We know how to enforce this constraint. It's an LMI constraint. This is an equality constraint, so we can also enforce that. And so we can search over and this is given, finite. Assuming we abandon the squares because the squares are already in here, so we can just get rid of those. Finite set. If we drop off the squares. Right. So then now we have a set of valid inequalities which we can search over, right? So this is anything here in this cone we can add to the representation of the set, and we don't change the set, right? So we have a way of searching for functions which are valid inequalities, and therefore functions which are positive on the set. Right. So if we write this out, right, as a sort of more SOS type result, right, then what we're getting here are our variables SI, Rij, Rijk, right? Where, right, we have to include all possible combinations of the given representation of the set. So S, right, equals X such that Fi of X greater than or equal to 0. So we have to include all terms in the monoid, which come down here. Those come from the monoid. And then we have to, we add the SOS as variables, right? So we're searching for a representation of H which is linear in our variables. And searches over all the elements of the cone, right? Now, of course, what we don't know is whether this is conservative or not, whether the cone is a strict subset of the valid inequalities. And of course, this is affine in our decision variables, as we mentioned, and we can enforce the sum of squares constraint using SDP, as we talked about in the previous lecture. So this gives us a sufficient condition for positivity of a function on a set in terms of whether that function is itself a valid representation of the set. And it can be tested using SOS tools. Right. So as the last slide in this part A, right, I'll just give an illustration of this. Right. So suppose we have a polynomial, right, and we want to determine whether it's positive on the interval. And here we're going to be very smartly using the representation of the interval, the quadratic representation. You don't know why the quadratic representation is good, but you have to take my word for it. We'll motivate that in the next part. Right, so this is, there's only one function. One of the reasons, of course, is there's only one valid inequality. And so we have to search, so the question of whether h is in the cone becomes whether h equals a sum of squares plus another sum of squares times f1. Because there's only one f, so we don't have to include products. Right? So we have to search whether h equals that. And this is f1. And so actually you can search this and it's actually feasible, right? So you can there's a degree 2 sum of squares, which is right there, which satisfies this equality constraint. And the first one, S1, is 0, right? And the second one, second variable here is this. This is S2. And you can multiply this out and verify that, in fact, actually, these two are equal. Right. Note that, of course, if we had used the linear representation of the same set, right, we would have had two valid inequalities, F1 and F2, which would actually dramatically increase the number of terms in our SOS problem. So in that case, we would have had, of course, the one we had before, and then we have to include a multiplier for the first inequality, right? That's the first multiplier. A multiplier for the second inequality, that's the second multiplier, and a multiplier for the product of those two, right? Because we have to include every term in the monoid, right? F1, F2, and then F1 times F2, right? These come from the monoid. Right? And then we have a multiplier for every term in the monoid to get our sufficient condition at this point for representation of the set. So again, representation matters in several senses. First of all, because this one has more variables than this one. And there are other reasons as well. And actually, of course, we had to include this as a valid inequality when we were representing the set, as opposed to just the linear ones. And actually, that's important because actually, in the linear representation, if you neglect this one, if you're searching for a validly Lyapunov inequality on an interval, for example, and you don't include this product, your SOS problem will likely not be feasible. So this product term, which is not less obvious, is important and necessary. And that's one of the reasons it's better to use the quadratic representation, because there's only a single one, a single inequality. And so I'm going to take a pause here and come back and show that under certain circumstances, the condition we just outlined is actually necessary and sufficient condition for positivity on these sets.